What if I told you that this mass of pixels is a photo of a person? Well, you'd likely agree, because we can clearly see the contour and other body parts that can be remodeled even by hand. Moreover, a clear pattern stands out because the image has visibly been subjected to some sort of effect. What if we pull out even more images of varying triviality? There is obviously no palpable or algorithmic method of extracting the unmodified version. For example, in certain areas, we can only notice a vague silhouette. But what if we switch to a different strategy that's going to let us reconstruct the original image by introducing synthesis and generalization? Let's analyze several ideas that we are going to employ to get the solution. First of all, we assign a score to each patch of pixels that tells us how important it is for it to look the way it looks, or essentially how real that region is. Imagine these scores as a map where height shows how real an image looks in that spot. The Lipschitz constraint is a rule that prevents sudden jumps on this map. It links the score to pixel changes. If you change a few pixels, the score only moves a tiny bit. I think I've made enough inklings to reveal that the core plan is to use generative AI. Within this system, the generator acts as the artist. While the critic builds the sheet of importance and evaluates the landscape, the generator's only goal is to fool the critic into thinking the produced image is authentic. The generator is built upon several ideas. It uses an encoder to compress the image into features, a bottleneck where we apply pretty significant noise and residual blocks, and finally a decoder to reconstruct the image back to its original size. By the way, the discriminator also uses a certain amount of Gaussian noise. It serves as a way to slightly weaken it. I tried setting it to extreme values such as 0.2 or 0.3, but I found a balance argument to be optimal. After a lot of testing and experimentation, I finally achieved the perfect state of my model and began noticing pretty promising synthesis. For example, here's an image where you can't at all see the original face, but the reconstruction somehow manages to come up with it. If we're talking about less distorted instances and essentially what the entire thing has been designed for, then we can clearly see it modifies the general expression a tiny bit. Moreover, even though the nose is changed, it still conceptually remains a nose, which suggests that it understands the underlying manifold of a given facial feature without exactly memorizing the pixels or specific variations. I'd like to dedicate the final part of the video to how exactly the constraint we've mentioned achieves its goal. First, let's recall that a convolution layer uses channels to scan for patterns. Each channel has a 4x4 set of multipliers, or at least that's the case in our situation. As this block moves across the image, it multiplies each of its 16 numbers by the 16 pixels directly underneath them and adds the results together. If a high pixel value is multiplied by a high multiplier, the resulting scalar is a high score. If that same pixel is taken times something small or just 0, the result is a low score. By setting these multipliers to different numbers, the system can mathematically detect where specific shapes appear in the data. Spectral norm stabilizes this process by imposing a limit. It computes the maximum scaling factor of the layer and divides all weights, or multipliers if you will, by that value, forcing the maximum gain to be exactly 1.